In the today's session, we are going to talk about the concept of the regression. Uh, okay, so because we are getting the questions like, maybe from the metrics, like we have seen some of the metrics related to the earlier session, maybe in the classification or regression or something like that. But now, while going through the topics we have covered, and regression was left over actually. So in terms of classification, to clarify with you, so let me give you the things whatever we have seen earlier. Uh, in terms of classification, these classifications basically we started with the k nearest neighborhood, and thereafter we have seen some sort of support vector machine, and then naive Bayes. Thereafter, we have seen some sort of, of neighbors. We have seen decision trees, and then we did observe the random forest. Okay, so some other aspects are also there, guys. Those things are nothing but artificial neural networks. And then we are having some other thing which is most famous, logistic regression. Okay, so I can cover logistic regression straight away, but I thought of maybe covering the regression first, and then we'll go back and study the logistic regression. Okay, so let us have a look on the regression. So regression, again, before going to talk about what exactly the regression is, as a data scientist or as a machine learning engineer, we always try to get the appropriate aspects, like, which are all the types of the regression. So basically, we study the simple linear regression, and second one is multiple or multi linear regression, and thereafter the third one is polynomial regression. So which is, of course, friends, which is a typical case studies actually. We'll be having some sort of the case studies like where we can manage the things with polynomial orientation. We'll come up with some analogy to understand. Simple, multiple, and polynomial. And of course, there are certain aspects, friends, actually. Regularization and penalization, actually. So that we are having lasso and then a ridge, and thereafter we are having the elastic net. Friends, in the day-to-day posting of the material also, I have done this analysis, but these three things predominantly used for the regularization and penalization. Okay, regularization and penalization. So if you consider the appropriate algorithms, maybe we need to handle some sort of analysis on the hyperparameters. The most important thing, again, if you are referencing the data pre-processing aspects, okay, not only for the certification, but in the projects, friends, we need to handle many aspects such as missing value imputation. This already we have covered. And the second thing is encoding techniques. Encoding techniques. And then we are having some sort of other things like, scaling. and then normalization. Of course, scaling may be either the normalization or standardization. Okay, something like that we are having. So, and one more important thing is uh, apart from this data pre-processing, after the model implementation, maybe if you are considering the model, we need to fit the model, and thereafter we have to maintain the appropriate predictions related to that model. Predictions means, guys, one simple analogy, and of however, in the today's regression session, I am going to give you which are all the best predictions and all. So in that particular case, guys, just say original data would be there, and we need to compare that original data with our model data. So if there is a less differentiation, then that becomes a less error. And if error is less, then our model is good. General, na? So whatever the original data we are having, up to that extent, if I could able to perform the model, then definitely will handle that convention. Okay, so that is what how you can refer. So the and one more thing is which is most important thing, guys, after the model actually. After the model implementation, already I have given the distinction model versus algorithm. Algorithm is the standard thing, and the model is nothing but whenever you are making use of that algorithm so as to achieve something, then you can say that as a model. Okay, so this model generally gives that fitting of the model, and thereafter where we need to verify the appropriate model whether it is performing or not. Related to this particular model, if you recollect, friends, there are certain aspects, training and testing actually. Training and testing. So simply what we'll do is suppose we are having 100% data, and this data will be split into 75 and 25. So 75 training data and 25 test data. Okay, so training just will fit our model. Okay, whatever the data I'm having will fit that. And upon this particular test data, we are going to predict, evaluate the model. We are going to evaluate the model. Now the point is, so just if you are referencing, after that, if I am getting only 80% of the accuracy, then I need to, I'm having two options. I need to iterate the data pre-processing, or else I have to maintain the hyperparameter tuning technique. Okay, either of these two can be observed, maybe data pre-processing or else hyperparameter tuning. And one of such kind of hyperparameter tuning techniques are lasso, ridge, and as well as the elastic net. And one more point, guys, if you remember in our earlier discussion, like in the missing value imputation also, in the missing value imputation also, we have used some sort of regression. Okay, if you are observing, we used that logistic regression, and we imputed the missing values. We imputed the missing values. Now consider this scenario. So like in the model, just I am consolidating all the things. We are having the data, and we are performing some kind of the data pre-processing. Okay, with all the means of this thing, like missing value imputation, encoding, standardization. I'll compose one more topic on this, guys, and the standardization and normalization. high level things we have seen, but again, so missing values, encoding, standardization and normalization, all these kind of the things. Scaling can be done with either standardization or normalization. Apart from these kind of things, this is step one, data pre-processing. And once this data is, we feel data is ready, then you can model creation, which is nothing but the fitting of the model by selecting the kind of the algorithm. Just you can select the algorithm and all. And once that model has been created, just you can uh, predict, or you can evaluate the model with certain sort of the metrics. If the performance is not up to the mark, then what we'll do, friends? The third one, this is the fourth step. The fifth step is okay. Next, after this thing, either you can connect with the second step. Again, you are going to apply the pre-processing, or else you go with the hyperparameter tuning technique. In either way, so just we are going to achieve the betterment of the model. So that is the understanding. Okay. So this lasso, rich, and as well as elastic net, all these are the techniques of the regression, but still we can make use of regularization and penalization so as to empower our model, and we can achieve the better results. Okay, that is the first point. You may have some doubt here. So how do I use an algorithm so as to perform the hyperparameter tuning? To answer that thing, if you remember the earlier session, for the missing value imputation, we did use this logistic regression. We did use that logistic regression. So with the usage of that logistic regression, we have done some sort of, and we have seen some kind of improvement also. If you consider, yes, I'm having that evidence here. So finally, in the analysis also, if you consider, friends, 74.3, deletion of the column, deletion of the row 82.3, a mean 77.9, and then we have seen that logistic implementation, which is greater 83.6. Okay, so that means if you are though they are algorithms or whichever, but still you are going to make use of the convention, like I can use another algorithm as a missing value imputation. Similarly, we can use these lasso, ridge, and as well as all those things as the kind of hyperparameter tuning techniques like regularization and penalization. That is the background. Now, let me jump into the aspect of the regression. I have compiled some aspects for us for our session where I can make use of those conventions to explain the concept of regression. And guys, apart from those kind of the conventions, we're having some more regression techniques to notify those kind of things. Just let me pull those aspects also. 1 minute. Okay, so just if you refer, okay, this is how you can observe the types of the regression. So simple linear, multiple linear, polynomial, stepwise regression, which is very, very important for the dimensional reduction. That's what I said. Some of the algorithms can be used as a hyperparameter tuning or pre-processing techniques. And especially if you observe, friends, in the beginning of our sessions, dimensionality, curse of dimensionality. There is a phrase called curse of dimensionality. Now, if you consider this dimensionality kind of thing, assume that in my data, I'm having 100 dimensions. And those particular dimensions, which are really causing some troublesome, where we need to observe, okay, whether really those particular kind of the things are available, or whether those things should be used or not. Okay, so that means if you are considering the number of dimensions, and we have to see that whether which are all the real contributors, and the real contributors we have to keep. So in a way, our final whatever the final aspect I'm having, so it should be leading to the better predictions. Okay, unnecessarily we are keeping all the 100 dimensions and we are unable to get even 65 or 70 percentage of the accuracy, then it leads to some disturbance, and which is the curse of the dimensionality. So for that we're having the stepwise regression. Periodically I will talk all these particular things because really they are very important narrations, guys. Okay, which are really help us not only in the certification but in our projects also. These things definitely helps you. Apart from those conventions, we're having the logistic regression, uh, where this particular logistic regression really belongs to the classification technique. Why it is, one thing, yes or no or true or false kind of thing belongs to the logistic. And though it is a name logistic regression, but still it is giving us some yes or no kind of thing. So it is classification technique. Whereas all the things they directly give some value, number or some sort of the value to notify you. Just here I have given the example of the prediction of the sales, stock price, temperature, house price. I cannot say if I am asking you like what is the house price in so and so area, maybe near to Annanagar or maybe near to some Yelahanka in Bangalore. Like that, we are having some various locations. And if I am asking you as a native of that particular area, so if I am asking you what could be the house price, you cannot say yes or no, because you should give maybe around 50 lakh or 60 lakh or something like that. So it's a number, it's a value. So obviously regression belongs to a supervised machine learning technique where the output variable is continuous. Okay, that means prediction of the sales of the product, stock price, temperature, house prices, all these kind of the conventions. Sorry. And then, as I said earlier, lasso, ridge, and elastic net regression. These three also belongs to the regression techniques, but we generally use them for the sake of this thing actually. So regularization and penalization, which is very important thing. So importance in the sense, just you can make use of these techniques so as to handle the hyperparameter tuning and so as to understand the data in a proper way. So this is how you can refer the orientation of types of regression, right? Okay. Now, moving ahead, so just if I want to observe, so now just we need to study about what exactly the linear regression and how do I refer the concept of the linear regression. Let me give you the compilation. Here the linear regression gives the usage of. So observe guys, is a way of finding out the relationship between a single continuous variable called dependent or target variable and one or more variables, continuous or not, is the independent variable. That means suppose what I'm doing here is I'm giving my experience and I want to get what is the designation I will get based on the experience, or else I'm giving the qualification and what is the salary expectation related to this. So this qualification and salary, of course, salary is a dependent on the qualification. This is the independent. We know that these things, na, independent. Generally, independent variables we refer by X, dependent we refer by Y. Okay, so now you see here experience also will be referred by X and we are finding out the designation we refer by Y. So these kind of the conventions can be helpful so as to observe, so as to establish the relationship between an independent variable and as well as the dependent variable. Now again, let us read this statement. It is a way of finding out a relationship between a single continuous variable called dependent. This is the dependent variable, as I said, dependent, or this is also known as the target variable because we are trying to find out the appropriate outcome of the target variable. Just we are making use of that particular convention. And then the independent variable, okay, one or more, maybe target and one or more other variables called independent variables. And here One we are using for the sake of linear regression or simple linear regression. Simple linear regression in the sense I'm having some x1, with that I am going to find out y. Whereas in multilinear regression, one simple analogy is y, but I'm having multiple values. Okay, so to give some example of the multilinear regression, maybe I am finding out of the house price. Okay, with respect to a number of rooms, area, and some kind of the square feet like that. Na? So some sort of parameters would be there for every problem definition. So here also we are taking about these particular parameters and we are going to find out the appropriate outcome. Okay, so these kind of the aspects really helps us guys to observe uh, how to find out the house price based on the number of rooms, area, and square feet. This means if I am converting this into a more generalized way, x1, x2, x3, all these are nothing but the independent variables and they are finding out the dependent variable. And this kind of the approach is known as multilinear regression. Okay, so this is how you can observe the understanding of simple and multilinear regression. Okay, so moving ahead. So just if I need to give some reference diagram, which is very important, guys, just to have a look on this because this is the diagram where you can explain your entire analogy of the regression model. Okay, so now uh, from your school days, maybe you are having the understanding of y is equal to mx plus c is a line equation actually. Slightly what we are doing is y equal to a plus bx kind of the thing we are doing. Now if you observe this thing a and as well as the equation of the line actually, I'll tell you guys what is this line and why we are using this x and y coordinates, all these things. But just to see that the line equation related to the y equal to mx plus c or y equal to a plus bx. So just it is giving some sort of the relationship between x and y. But that time while explaining by our professor or teacher, they won't consider those points. Just they just give us some sort of understanding of this line equation, and they generally prefer the usage of this is the straight line equation. You go through the lines and go through the some examples. Now you can simply connect the dots. The way how we are making use of this straight line equation is there are two variables x and y and we want to establish a kind of the relationship. Now you see, so x value and as well as the y. Let me put in this way. Suppose I'm having some sort of the x values and as well as the y values. As I said earlier, experience and the corresponding salary maybe. So experience 2 years, 4 years, 6 years, 9 years. For the experience of the 2 years, maybe I will be getting some $1,000. Okay, this thing. For the experience of the 4 year, maybe we are getting $3,000. Assume that 4 years. For the experience of the 6 years, maybe $9,000. Okay, somewhere here. And for the experience of 9 years, we may be getting $15,000. Assume that. Maybe we are getting somewhere here. Now, what we are doing here is just we are combining these things. Okay, obviously, just we are making use of some kind of the convention. Here the intersection point, and here also we are having some sort of the intersection point. If you draw a line related to this thing, guys, just it is a line kind of thing. Okay, the same thing now here. Just we are seeing the line. Okay, maybe some x values and y values are intersecting on that. The analogy. So this way. But that time we never feel this kind of the connect. That is why we see this thing as a kind of the line equation. Rather, what you can observe is Now you see here it is pretty simple. Corresponding to the experience value, I am having the salary value. There is a kind of the relationship between this line. Okay, this line is giving the relationship between uh, x and y. And we can generalize this. Maybe from this particular diagram, I don't have the salary value for 2.5. I don't have the value for 6.9 years of experience, or I don't have the value for 10 years. Because why we are doing this kind of the analysis is, if you are able to fit your algorithm to your known models or to your known data, then after fitting this particular data, maybe you can make use of the convention, like later point of time I can able to leverage, I can able to extend that particular functionality to unknown variables. Okay, many people may ask you, so we are having some data. On top of the data, you are fitting your model and you are testing the efficiency of your model on the original data only. Then why? What is the reason or why? Reason is simple. If I'm estimating the known data and how my model is performing, then I can able to understand the efficiency. I can able to observe the efficiency, so that as I'm having a solid model with certain expectations of the prediction, proven model, that too. All precautions we have taken, like data pre-processing we have done. Okay, all the hyperparameter tunings we have done. Okay, now friends, and then now we are using this model to test the new data. Then obviously on top of this new data also, unseen data also, your model is going to exhibit some sort of the outcome. So that is how you can refer the usage of these kind of the models and data, whatever I'm having, right? So this thing, guys, really plays a vital role in the understanding of the relationship between the two things. That is the actual essence of the regression. If I was asked to establish a kind of the relationship between the variables, maybe dependent and independent, in terms of our machine learning or data science perspective, just we can say as the independent and dependent, independent xy, x1, y, x1, x2, x3, like that, dependent y, target variable. So just the main theme behind this particular regression is just to establish a kind of the relationship between the independent and dependent variable. And for that particular purpose, we are going to depend on the this line equation. Okay, now hope you can connect the dots. Now the change, friends, actually, so from this point to this point, some sort of the change is there, na? Change in y actually. How if I'm keep on increasing the x value, how the y is getting changed. Maybe probably we need to observe those particular things where those things are greatly gives us understanding of our model. Now some more measures are there, friends, and these measures gives that some sort of the understanding where if you are referencing these particular things, just have a look on this, which are all the references of those variables. Now you have a look on this. Where y is your dependent variable, we know that from our experience. X is of course independent variable. B, because y is equal to ax plus b. B is your slope. This is the slope value. How much the line rises for each increase in x. Suppose if x value is 5, okay, how y is rising? And if x value is 10, then how is rising? Y, whether positive or negative rise, whatever the things. Is there any real correlation or is there any real changes there between that x and y? That can be observed with respect to the B. And whereas if you are referencing the intercept value, intercept, guys, here, suppose if I am putting x value as 0, then entire thing becomes 0. But my interest is what is the I have to start somewhere, na? So if you see the diagram, okay, so just we are starting somewhere here, because without knowing x value also I should start somewhere. This is the intercept value, actual value, base value. See, a is the intercept, the value of y when x equal to 0. When x I am not giving anything, then obviously, see, if the person who is not having experience also should have some basic salary, na, that is why actually. So, but how do we get that? If I am putting x value as 0, my entire equation is becoming as 0. But whereas if I want to maintain that convention, definitely based on that a intercept the value of y when x is 0. If it is 0, even I don't know the change in the because b is nothing but change of y according to x. But I am saying my x is not there here. Then how do I estimate this y? For that I can use the a value, which is the intercept value, which is the intercept value. Now, these points we need to be very cautious, guys, because though they are very simple, but finally we need to come up with the analogy of making use of the convention. Now, I'm giving you some sort of typical equation where like, rather than using a, b or something like that, in our data science or machine learning kind of understanding, we'll be taking some y value, beta naught, beta 1 x1, epsilon. So this is a typical uh, line equation where we are going to use in all our simple linear, multiple, polynomial, all these kind of the conventions. So just to think through, guys, how the transition happened. First, we have seen y is equal to mx plus c. Later, we taken this y is equal to a plus bx, making sense because even x value is not there, but still we are able to have the a value, which is initial y. Though I'm not having the x value, but simply I can make use of that a value, and in a way we can compute that y value also. That is main important point. And once you observe those kind of the conventions, now a typical kind of the terminology in line with the in line with your algorithmic aspect, maybe independent, dependent variables. Okay, y of course is the dependent variable, target variable, and our beta naught is nothing but y-intercept. Just now we have seen a plus something is there, na a, like that. And if you are referencing the beta 1 x1, your x1 is of course independent variable, and we are having a separate topic, friends, how to compute the coefficients, how to compute the beta values. Excellent topic, guys. I will be covering in a while. In the sense after completion of this SLR and MLR, just we'll see how do we compute the beta values also, because that definitely helps us to empower our model related to better performance, okay, predictions and accuracy. Now, you observe here the beta one is something like population slope coefficient, COE, coefficient value. So suppose if I am taking y is equal to 2x plus 3x square plus 5x cube, something like that I'm having. So these are all coefficient related to the corresponding equation. Okay, so similarly here also beta 1, suppose if I'm taking multilinear regression, a simple one more component I need to add, like yi equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, something like that it goes on. And most importantly, suppose in the implementation of any algorithm, our model should give the correct performance or accurate performance. Correct or accurate performance in the sense, guys, if you are referencing some sort of the performance measure or error estimation, if your model computed data is having more difference compared with the original data, that is the error. Na? Error in the sense, what is the we are having certain original data, and of course we are having the model data. And if you are estimating, if you are computing the distinction, if the distinction is more, then your model is having more error because it is deviating to the original data items. Whereas if your model is not having more errors, then it is very nearest to the corresponding original data. So that is referenced by random error component. This is the random error term. Error should be less or more. Error should be less always. It should be less. If you connect the dots, I have given that root mean square error, root absolute error, R square, adjusted R square. All these are the things related to the measures of the regression. measures of the regression. If you are referencing one more point, the classification kind of thing. Now these classification friends actually something like we are having some confusion matrix, and then we are having AUC ROC, and we are having accuracy, precision, recall, all these kind of the conventions. So your metrics generally estimate the erroneous condition or error situations, because we cannot directly go and verify each and every variable and find out the distinction, original data minus model data. We cannot do that. We won't. But only the thing is with some sort of the measures, if I'm working with the regression model, definitely I should use the root mean square error, root absolute error, R square or adjusted R square, all these kind of the conventions. Whereas in the classification, confusion matrix, AUC, ROC, accuracy, precision and recall, all these are the kind of the metrics where you can venture, you can verify whether your model is really doing well or not. Now coming back to our discussion, if you are referencing this epsilon, which is random error term, or which is also known as random error component. Why we are saying this as a linear component is, guys, observe here, both your simple linear regression, multiple linear regression belongs to the linear models. There is no separate model for the a kind of SLR and MLR. Both belongs to the linear model. Whereas if you talk about the polynomial regression, okay, now guys, polynomial regression, this is not a linear model. Okay, so polynomial model, because that is containing some square terms and all the complex kind of thing, is a non-linear model basically. Okay, which is not a linear model, is a non-linear model. Okay, so obviously guys, just if you observe the polynomial kind of thing, where it is some sort of observing non-linear kind of the functionality, where there is a possibility of handling the square values, cube values, all those kind of the convention. As I promised earlier, definitely I will bring some case study related to the polynomial regression, which definitely helps us to understand the motto behind this regression models, right? Okay. Now, one more important point, guys, here. So once we conclude this particular equation, the other points are how do I observe? So what is the distinction? How I am making use of estimation of these particular values. Now, if you observe as a kind of the convention, uh, here I am giving some diagrams, guys. So observe just this particular diagram gives that I'm having the independent variable X and dependent variable Y. This is a standard notion followed everywhere, is a mathematical representation where your independent variable and dependent variable, this is the line of relation. This line generally gives that in the first graph, just we are getting the less error. That means our original data and all these kind of the things are very near. Whereas your second graph is a bit erroneous kind of thing, more error conditions. Because this particular line, there is a certain deviation. Okay, so related to the original data items. Actually, our model and corresponding deviation values you can observe. Okay, there are certain more errors are there. These distinctions are nothing but the errors. Na? As I said earlier, what is the difference between the original data and as well as whatever the implemented values with our model? So just our model has implemented something and we got some sort of outcome, and we are going to test that particular outcome with respect to the existing values. Then in that case, guys, just you need to emphasize on this minimization of the error. So maybe if you are implementing the simple linear regression or multilinear regression, in either of the case, you have to think through like how do I reduce my error in terms of these original and computed values. This is how you can make use of the convention. And of course, guys, just if you are referencing the multilinear regression, just there is already have given the introduction. But still, if I need to properly address what exactly the multilinear, have a look on this guy. Just there are multiple values where when you have multiple independent variables, I mean x1, x2, x3, multiple independent variables where these things are referenced by one dependent variable. Then we call it as multiple linear regression, square feet, number of bedrooms and location, brand, floor rise, etc. Whereas if I want to find out the house price, okay, assume this is a house price. Already I have given this example and we are having some square feet and number of bedrooms and location area or something like that, and some more options might be there, x4, x5, like that. So all these independent variables are there so as to verify the target variable or dependent variable, right? That is how you can see the observation of the multilinear regression. And of course, if you consider which are all the parameters I'm going to use, those parameters are like this guy. Just I am having certain number of parameters. Already we have seen these kind of the parameters in our simple linear, but still, okay, definitely. While understanding this regression kind of thing, we should be very careful about all these kind of the things. Here, just you see y equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on beta n xn. If you see the terminal, this is the residual error. Most important term, guys. Residual error, which is nothing but the difference between the observed and estimated dependent variable for the particular observation I. Observed value, estimated value. Observed value, original. Estimated value, your model estimated something, na? So the difference between observed and estimated dependent variable, definitely this particular residual error must be less. Okay, if you are having more error, then your model is highly deviated. You need to handle the hyperparameter, all these kind of the convention. Now, if you consider the independent values x1 to xn, any number of independent variables might be there. So these are all characteristics. Sometimes they are also known as the Bayesian characteristics. Okay, based on those particular values only, we are going to compute the values. And y, of course, your independent variable estimated, whatever the value we are estimated through the model statistic. Okay. And these are all the coefficients, as I said, beta naught, beta 1, beta 2, all these things are the regression model coefficients determined in the analysis. So according to the kind of the magnitude, those kind of the conventions can be observed related to the regression model, right? Okay. So this is what how you can make use of your regression model and trying to implement the orientation. Moving ahead, some other points I need to give to you. Always one question remains, friends. As of now, just we have seen that line equation. And if you consider this example, this is the line where we are making use of establishment of some kind of the relationship between the dependent and independent. Now, how do I say that this line is the best fit line? Because the importance here is your entire regression is revolving around the line equation. And if you can able to say this is the best line, then obviously we can observe that line as a kind of narration, just you can make use of that convention. That line must be representing the best fit line. Best fit line is nothing but whatever the line generated by the regression, it is making use of reducing the error. So for that, just I am making a kind of consolidation. Whatever the points we have discussed, they should make sure that okay, how to find the best regression line. Probably this is the best thing where you need to expect, from all your regression models. Okay. Now you see guys, we discussed that the regression line establishes a relationship between the independent and dependent variables. I'm having the independent variable and there is a relationship between the dependent and as well as the independent variables. This is of course, regression line established relationship between these two. That is the basic thing. Second thing is a line which explains the relationship better is said to be the best fit line, of course. In other words, the best fit line tends to return the most accurate value of y based on x. So we are, however, giving the x values related to this x value, I need to compute the y value. And if your y value is most accurate, if your y value is most nearest to the original value, then I can say that is the best fit line. Cause a minimum difference between the actual and predicted value. This is what you call the lower prediction error. So suppose if I'm having 5 years of experience and I want to find out my designation. Okay, I found out that. And then 10 years designation. So I can make use of this as a generalization. Then I can find out the kind 6.5 years or is it even 12 years also. Practically, these two values are not there in our both training and as well as the testing. Assume that. Okay, of course, in the prediction, of course, we are using the testing. But later point of time, even from our other values also we can compute. Okay, where the data is not from your training or testing, but of course always you can perform some sort of the activity other than the training and test values also we can perform the activities, right? Okay. So this particular best fit line is something like which is used to reduce the error, lower the prediction error that you observe, guys. That is the most important understanding. Now we are revisiting our diagram actually. So this particular diagram is most important. Now you observe that x and y values remain same, that we are not going to change anything. Now this is the line and this is the value which is, and this is the computed value, maybe actual value or something. And you can observe related to the actual value and as well as error. So this particular model, this is the line generated by the model. And whereas if you are considering the points which are surrounded by that particular line, they are the actual values. They are the original values. Okay, now friends, now what we are doing is we are computing a kind of the differentiation between the predicted value, nothing but estimated value, and the original value, observed value existing. Now just to observe this, this gives that error. Error means whatever the predicted value I'm having compared with the actual value, if there is a differentiation, then there is the error. Assume that, guys, we need to spend some 5 hours of the time in learning. Assume that in a week, just you plan accordingly. You planned accordingly, but only you could able to, due to your busy schedule or something else, you only spend 2 hours of the time. So 3 hours error. Whereas if you are 5 hours and you could able to spend almost 4.5 hour, only 0.5 hour, that is 30 minutes. Of course, you can manage. Okay, so this is, if error is more, automatically you are deviating the values. You are deviating from your original data. You should not do that now. So definitely that your model should be in such a way that just it need to verify. Okay, whatever the implementation I have done, those particular kind of the convention should provide us some sort of the convention, like we want to minimize the predicted value and actual value. That is how you can say the error. Okay, now there are certain aspects where we need to observe. Most importantly, but one more thing, these things are asked in our certification also, guys. So I observed twice. Now, if you refer this particular point, kind of the errors. Now, if you are considering what are all the erroneous kind of the conditions, just if you are observing the usage of these kind of the things, like there are three sorts of the errors related to this convention. Sum of all errors, like we are computing that actual minus predicted, and we are summating all these things. Sum of all errors, that is known as sum of absolute value of all errors. That means maybe if I am getting the negative values and I want to modulate that. Okay, just I can use the absolute value where if I am applying the modulus, then obviously this negative value will be converted into the positive. So just I can say that that is the differentiation between original value and predicted value. Now the most important thing we generally prefer is squares of errors, sum of squares of errors. Because guys, here why we need to square the error is if you consider guys, suppose if my error is very less, okay, no problem. Even if I am squaring also, it becomes less only. If my error is more, maybe two differentiation, if I am computing the square, it becomes 4. That means I'm giving at most attention to my errors. I'm giving at most attention to my errors. I am magnifying my error in such a way that if a developer or if a data scientist or if a machine learning engineer, if you want to observe, if you want to identify the sort of the errors, okay, if you are giving the due respect to the errors, and if you are able to handle the errors in a most efficient way, then obviously you have done your work. That means whatever the model we have implemented, all those kind of the conventions are having some sort of good predictions and accuracy. So if I'm getting some error and which is more, if I'm making use of square, then definitely I have to worry about that because there is a lot more distinction between the actual value and as well as the predicted value. So I need to perform the appropriate convention related to the approach. Okay, so this is what how you can make use of the convention of estimation of the errors. Okay, now apart from these kind of the conventions, I have given you some sort of estimate the beta coefficients like beta naught, beta 1, beta 2, all these things are there. Na? So probably I will conclude. Don't worry, friends. We are we had more kind of the discussion today, but it's okay. No problem. Just you prepare and come back to me if you are having any error. The members who are seeing the recording first time, but still no problem. You can come to me. No problem. I'll clarify the doubts. Now have a look on this, guys. Estimate the beta coefficients. So your beta coefficients are nothing but beta naught, beta 1, beta 2, all these kind of the conventions. Now there is a most commonly used kind of the construct is ordinary least square method, OLS method. Okay. This OLS method, what it does is the objective of this OLS is to minimize the sum of squares of residuals. Sum of squares already we know, and we are summating and we are making use of. Okay, so whatever the value I'm having, we are summating all those things. Where how do I find out the error? Standard equation y actual minus y prediction whole square. So because we are having the actual values and we are making use of the difference between actual and predicted values, and we are making use of the squares actually. And where your beta equal to inverse of, okay, just it is a mathematical kind of thing. Just we are is using the matrices kind of the format. Don't worry about that, guys. But just to observe this point, your uh, ordinary least squares method, which is used to minimize the things, and there is a direct functionality OLS kind of thing. Directly you can apply maybe in the stat models or whichever the metrics you are applying. So just to feel that y original minus y prediction whole square. Okay, like that you can manage. And most important aspect in the estimation of the beta coefficient is the gradient descent, which is very, very important. Maybe in the deep learning projects also, we can make use of this gradient descent kind of thing. Now observe here, guys. So gradient descent itself needs some definitely 1 hour I will take, guys, on this gradient descent as we are getting some questions on this thing also. But as the scope of this session is to cover the linear and simple linear and multiple linear, and as we are talking about this errors and all, just as a part of that estimation of the beta coefficients, we were talking about these things. So in the gradient descent kind of thing, we are starting with the random value for beta, derivatives. There is a reason, guys, why why I need to derivate dou by dou x kind of thing, all these kind of things. The differentiation, if you are observing the derivations and all, maybe in your mathematics and all, you would have that derivations, which is giving the slope value, friends, actually. So in a typical regression, slope is playing a vital role. So we want to find out that particular slope, and which is a deciding factor how your x value influencing the y value, because if you are changing the independent variable, how it is reflecting in the dependent variable. And most importantly, the learning rate, alpha. Okay, so we are talking in terms of alpha and beta. Whenever we are dealing with that gradient descent kind of the aspect, definitely I will introduce all those kind of the conventions. Now with this, in the next session, I'm going to talk about the logistic regression with this kind of the background. Now we are able to understand what is the regression and what exactly that. After completion of this logistic regression, the most important things are assumptions in regression. Assumptions in regression. Assumptions, friends, in the beginning of the machine learning kind of aspects, we have seen two things. One is parametric, another is non-parametric. Okay, so parametric versus non-parametric. Parametric in the sense there is no assumption. I'm sorry, non-parametric means no assumption, as the name implies. Parametric means we are having some sort of assumptions. Okay, there are some preconditions and prerequisite and wherever regression model should satisfy though. So those kind of the assumptions are much more important. 4 to 5 assumptions we are having in the regression model. Those things also I wish to cover in the next session, logistic and as well as the assumption. So now the key takeaways of the today's session. So just you observe here. We started with the understanding of the regression. A regression which is used to establish a kind of the relationship between independent variables related to the dependent variables in a simplest form. And then we are having certain types, simple linear, multiple linear, polynomial regression, and logistic we are not saying here. Of course, it is belongs to the classification. And thereafter we are having the lasso, ridge, and as well as the elastic net. So all these are the conventions related to your regression models. Okay, so apart from the typical regression usage, you can use this lasso, ridge, and elastic net for the sake of regularization and penalization. Now we discussed some line equation where that particular line equation gives y equal to beta naught plus beta 1 x1 plus epsilon, where is the residual error or erroneous term, and this is the simple linear. And in case of multilinear, a simple change, just I can make use of these kind of the conventions, beta 3 x3 plus epsilon, something like that. Now there are error terms. Okay, like just I can define y original minus y computed. This is one thing. And I can use the modulus operator, y original minus y computing. And third thing is, guys, just you can make use of square actually. Y original minus y computing whole square. Okay, and then thereafter, in terms of the beta coefficients handling, just we are having two techniques. Just now we have seen ordinary least squares is one of the technique, minimization of the error, and then gradient descent, which is most important, and of course which helps us until the deep learning, guys. It's not only helpful in our data engineering or machine learning, or until deep learning you can venture this gradient descent. So prepare well. So just I'll be posting these things in the chat. So have a look on this, and if you are having any doubt, just come back to me. And as usual, on the daily basis, also I'm scoping some of the aspects. Try to prepare, guys, so that you can have some knowledge. Okay, so with this, definitely we are going to just you can I'm going to expect that, like, you can implement in our projects, or even the certification also you can confidently apply. Okay, good. Okay, so that's all for today's session. Okay, thank you very much. Thank you, Deepika.